So I appreciate everyone's patience. I know for this slide section, we're on slide 56. It's Friday. This is the final demo. This is the EPPR frame. So this is a frame that I use a lot. It's a very versatile frame, especially in the Artemis era or for SMD missions where we've got a lot of complex missions going out to Lagrange points, which exist in the rotating frame of the CR3BP. But sometimes you need to up-res your solutions into higher fidelity. So ASSET Astro Library comes with the Ephemeris Pulsating Rotating Frame, so EPPR, and this model utilizes the same basis vectors as the CR3BP. So you are non-dimensionalized in the same way where P1 and P2 are connected by the x-axis, z is in the angular velocity of your frame. It's the exact same basis vectors of the CR3BP. However, it's adding the fidelity from the EPPR frame that we need to instantiate first to handle full ephemeris propagation. So we've even verified this propagation against a lot of the standard trajectory tools. We've compared it with Monty, compared it with GMAT, FreeFlyer, STK, Copernicus. We've got verified the dynamics of this problem where it's got full ephemeride. So even the frame itself can be pulsing because say you set up the Earth-Moon system, the moon is not actually circularly constrained in an orbit around the barycenter with the Earth. It has some eccentricity. So technically that characteristic length will change. That is all handled on the back end of the EPPR frame. So the EPPR, you always know P1 will be at your minus mu on the x-axis, for example. So it's a very useful frame where you can add in the ephemeris pulsing of the frame from your two bodies being in elliptical orbits, and you can add in the ephemeris perturbations of things like the sun or something like that. So while CR3BP is a simplified autonomous model where you get smooth periodic periodicity and structures that form from that can now smoothly lead into the ephemeris model where you can get real-world ephemeris output, but still have all the convenience that you're provided from the CR3BP basis vectors. One other useful aspect of this is since it's handling the change in scale in the backside and it's got the same basis vectors, you can formulate an initial guess in the CR3BP, and your states from that initial guess don't need modified at all to drop them into this EPPR frame. So you can have an NRHO for gateway, or you can have the James Webb Telescope initial conditions and propagate some of its manifolds in the CR3BP. You can take any of those states and use those as initial guesses in the EPPR without having to modify them for frame changes. So it's very versatile frame if you're working with any Lagrange point orbit type work. Again, EPPR is a ephemeris frame, so we need to instantiate a frame first to handle spice kernels, then we instantiate the model. So again, I'm obliged to remind you, the frame is only defined for the epoch range that you set because we're doing the spline fit of your spice kernel samples. So we get the convenience that we call spice once before the run, and now we don't have to call spice every iteration like some tools do. But now there's that added caution of you need to solve your solutions within the time span where your frame is defined. So import for this change, I know it's 410, so I think I'll walk through this example. You have the base code. Feel free to do this experiment on your own. So imports change. We're going to do the same problem that we did in CR3BP with an ephemeris. So now from Astro models, we'll pull EPPR and EPPR underscore low thrust. And from frames, we need the EPPR frame. So this should feel very similar to exactly what we did for going from the two body to the n body problem. So again, we're going to have spicy pie and we're going to have these date time functions because I don't think in terms of Julian dates, so we can let ASSET handle that for us. So for this example scenario, again, because I said we're sharing basis vectors, we can just read in the data that we saved off from our CR3BP solution and reconstruct the halo orbit, the low lunar orbit, and the low thrust transfer that we're going to use as an initial guess in the Ephemeris model. So we can unpack all of that. We configure our frame. So again, I've got a spice furnish. We're going to again instantiate 3141596 as our Julian date 0 and add in for this analysis. I added a frame time of 10 days. I believe the optimal was within 4 days maximum. So this is well within the defined region. So again, here, slightly different syntax from the CR3BP, just how the n-body model is different. We're passing in strings of the string of P1 because we've got spice under the hood, the gravitational accel of P1, the string of P2, accel of P2. We're using lunar distance as the characteristic length again. And then the rest of this is the exact same input structure that we had for the n-body model. So the starting Julian date and final Julian date of your frame definition, how many discrete samples of the spice bodies do you want for the interp table? And then this frame here is, we have some convenience functions in the EPPR model to convert it from rotating to an inertial frame. So this spice frame that you said is what frame defined by your kernels do you want your rotating frames to get converted to before you deliver it? Because most people, if you give them states and it's in the rotating Earth Sun ephemeris frame, they will ask you to reconfigure it. So same format as in 2-body. Again, we can add spice bodies, and now we're ready to instantiate the model using the frame that we've instantiated. So we pass in the frame and add alternate bodies. We do the same with the low thrust, but now we need the frame, the engine instantiation, and then the activate all bodies. And we can define our dimensionalizing terms again. So this next challenge that I'll talk through, it is at this point, especially going through the first 3 examples, this is a trivial challenge at this point. It's solve that same problem that you had in the CR3BP in the EPPR. So the hints are probably even just sounding repetitive now of, remember, models are used to create asset phases. So that's a reminder. You're going to use mixed model instantiations for the 2 different phases. And phases need initial guesses, but a reminder, we're using our CR3BP solution as the initial guess. So you can look at this code here, and this is of course in the solution, and really the only things that changed are we are now instantiating low lunar orbit as the ballistic EPPR and low thrust phase as the low thrust EPPR. We've kept that same transcription. We've added that same delta time, and we are essentially keeping everything else the same and flying out to the transfer in ephemeris. One other example flag that I put in here is you can set the line search mode and default it to L1. So that's an L1 line search method for your optimization. Here I'm doing it to set the solve. So setting SOE LS mode is for the solver. Setting OPT LS mode is for the optimizer. This is, again, is a setting exposed and documented more in the online documentation. And then we configure the forward link equality and we can run it and solve it. And we get a little bit longer of a transfer. So I know the change from 2-body to n-body was entirely trivial. Here we actually get, I think around 55 hours in the CR3BP. But once we include ephemeris terms and the pulsation of the Earth-Moon frame, we do get slight warping of the solution. It converges quite quickly, but you can see it's actually for this epoch when we want to fly this mission configuration at 3.1415926. It's going to fly out and take slightly longer than our idealized CR3BP. So do we have any questions in the room or online on this this problem?
So one just quick thing to bring up, the way you define your, if you go back a slide.
Yes.
EPPR. Yeah, so they're buried in there, the EPPR frame. 947. Yeah, 947, yeah, 3,000 points in the ephemeris month.
Yes.
So And kind of, I don't know if we talked about this in the previous part, but how those work is that's basically just an interp table, right?
Yeah, we
So-
covered that in the end body frame.
So one of the things I had problems with because I'm flying trying to hit the Earth, but flying really, really close to Earth or something like that. Sometimes you need that to be higher than that.
Yeah.
And so like the thing that I'm running right now, which is now running wonderful, I've actually cranked up to 20,000.
Okay.
And now the funny thing is it takes longer to create the frame because you have more points. But once you create the frame, it runs trivially fast. I mean, it's still, there's really no performance impact after you create that.
Yeah, definitely.
Yeah,
So
there shouldn't be.
Right. And so right, I mean, it's just an interp table. And so, sometimes when you're flying, way down the gravity well or pointed at the Earth as an example, you might need more than that. But if you're floating out in the middle of nowhere, So
yeah, no, that's definitely a good reminder. So all of the assumptions that we talked about in the the end body frame apply here to EPPR, where you want to make sure your number of interp points that you're passing into the SPICE table for the bodies is appropriate both for the dynamics that you're modeling and for the times range that you're setting for Julian date 0 and Julian date final. Yeah, very good point. Well, not hearing any other questions online, that is actually our last slide. So we are going to be concluding the training now. So thank you all for everybody sticking with us for 2 days, and definitely feel free to reach out to us at the lab or visit our documentation for more info. And I hope everybody's able to start applying ASSET to their problems.